Hello, welcome to Chapter 1 review. What we're going to do here is Chapter 1 was about describing data. So when we get data, what do we do with it? So first, we have to know what our data is. And it's either categorical or a quantitative variable. A categorical variable places individuals into groups. So say race. You can have uh, race as being a categorical variable because there's each data point is put into one of those categories. Whereas a quantitative variable would be like height. It could be 60 inches, 65 inches, 70 inches. All of that would be a quantitative variables, and we could do arithmetic with those to find mean and IQR and such. Now, when we describe categorical variables, the distribution of categorical variables, we usually have the, usually it's the percentage, and then the categories down here, like white, Asian, and so on, uh, for the races. And so it's the distribution of either the count or the percent, and it's usually percent um, of whatever variable you're testing here. You can do count, but typically you're not going to take the same amount from each category, so it makes more sense to do percentage. Now, when you're describing quantitative data, there's a lot more possibilities, like a histogram or a stem and leaf plot, a dot plot, uh, um, uh, box plot, or a ogive. Now, an ogive is probably the least common. You should have seen all of these other ones in previous uh, classes. Now, this is a stem and leaf plot, or sometimes just stem plot. Now, uh, this one, this particular stem plot splits the cells. So uh, 0, the first row corresponds 0 through 4, the second row corresponds 5 through 9. And once you do that, you have to split it all the way up, all the way down, so you can see the distribution of the data. One thing that's missing here is a key. So you have to write 2/4 equals means 24, and let's say that these are how many rows is sold on a particular day. So uh, you need a key for the data. Now this is a histogram. A histogram is different from a box plot. A box plot is used for categorical variables, and a stem plot here is different because the boxes are touching each other. There's no gaps. And uh, again, you're using quantitative variables rather than categorical variables. So this is a histogram. Now again, histograms can either be in counts, like this one is, or you can do percent. And when it's percent, it's actually called a relative frequency histogram. So if you ever see the term relative frequency, that's means they want percentages for the y-axis. Now this histogram is terrible because the histograms are not, the bins are not the same sizes. When you're doing a histogram, make sure your bins are exactly the same size so you see a good distribution of the data. This one is incorrect because there's gaps between the boxes. This would be a bar graph instead of a histogram. And again, like I said before, relative frequency histogram is using percent rather than counts on the y-axis. A modified box plot is a box plot that instead of going to the minimum or maximum, if there's an outlier, it marks it with a dot. So when you look at the graph, right away you see that outliers are present. A regular box plot would draw this all the way down to that point. Now, here we also know that the next data point up is somewhere like 16. Hopefully this isn't percent, because that would be a pretty bad test. But we also know that 25% of the data is below Q1. Here is our Q1, and then 25% of the data is before we hit the median, and then 25% of the data is before we hit Q3, and then 25% of the data is at your max. Now, keep in mind, just because this is a longer space doesn't mean more data is here. 50% of the data is below the median and 50% is above the median. This just means there's a lot more people in a smaller area. Now, if they asked about a mean from a box plot, since this is skewed to the left, the mean would trickle down below the median. We don't know exactly where it's at, but we just know that it's going to be to the left of the median because this is skewed to the left. Now, this graph is bad because this is asking what's wrong with the graph, because this represents 5 and this represents 5. Whenever you draw a bar graph, make sure you start with your scale and go up by that scale. Once you have your scale out, then start drawing your box plot. A dot plot, this is pretty self-explanatory. Wherever there's a point, you just put a dot, and it's pretty easy for people to read and see dot plots. The ogive, or the cumulative frequency graph, adds up the frequency as you move along. So what this does, if you want to find the 30th percentile, you go to 30%, go over and down, and I would say 26 number of homework problems would be the 30th percentile. Where if you want to find the 80th percentile, we go here, somewhere around 30 homework problems is in the 80th percentile. Now, one common question with ogives is to find the mean, or the median. The median is at the 50th percentile, so you just go over and down. So the median in this graph is about 27 or so. All right. Now, when you describe data, you should look at the overall pattern and look at its shape, center, and spread. Or any deviation from that, like an outlier or anything that is striking. Usually what we say, we try to remember, is SOX. Shapes, shape, outliers, center, spread. I don't know why I wrote this in a different order. I should put outliers there, maybe. And outliers, think about anything unusuals. Even if there's a big gap in the data, make sure you mention that gap. Another thing that's not in SOX that you need for AP test questions is you have to write it in context. So you want to mention the problem while you're writing about the distribution. Now in shape, make sure you say whether it's skewed left, skewed right, or symmetric. When you're deciding on how to describe the center and spread, there's two ways you can do it. If the data is symmetric, we typically use mean and standard deviation. If the data is skewed or not symmetric, then we use the median and 5-number summary. And it also helps you, oops, that's not what I wanted. It also helps you when you hear somebody talking about the median, it gives you an indication that that data set, the population, is probably a skewed distribution. Whenever we compare two distributions, here's a side-by-side dot plot, side-by-side stem plot, side-by-side histogram. Now, whenever you're comparing these distributions, you always want to put them on the same scale so you can see where they're at. On the AP test, if they ask you to write a few sentences comparing the distributions, you have to do the shape, outlier, center, spread, context, and compare. So you'll want to say that you have to use a comparative word saying the length has a higher mean than the neck girth mean. The spread of length is wider than the spread of the neck girth. So words that compare the two distributions are also needed when comparing distributions. Now, mean versus median, the word resistance means whether it can withstand an outlier. So the median is pretty resistant to outliers because if you have a large data set, putting one outlier is not going to change the median very much. However, putting one outlier can change the mean uh, because the mean requires adding up all the numbers and dividing by how many values you have. So each point can throw off the mean. Uh, if they're exactly the same, the mean and the median are if the mean and the median are exactly the same if the distribution is symmetric, and in the skewed distribution, the mean's closer to the tail than the median, and we talked about that earlier. Now we have to look at the 5-number summary, and this is typically for skewed data. The minimum, Q1, median, Q3, and maximum, we talked about that a little bit earlier. 25% of the data is between each of those values. If we want to find outliers, we use the IQR, Q3 minus Q1, and we multiply that by 1.5 and add it to our Q3 and subtract it from our Q1. This is common, and a lot of people forget this, so I want to go through this. You have your 5-number summary. So this is your Q1, Q3, and your median. Now, what we do is subtract 29 minus 10 to get 19. So that is our IQR. So now I have 1.5 times 19. I'll take out my calculator. 1.5 times 19, 28.5. Now I have to add 28.5 to 29 and subtract 28.5 from 10. So from negative 18.5 all the way to 57.5. Anything within this range is not an outlier. So if I wanted to add an outlier to this data set, it would have to be above 57.5 in order to be considered an outlier. So if I added a 61, this would be an outlier. But anything within this range is not an outlier. All right, that's chapter 1. Now our chapter 2 is about density curves and normal distributions. And the first thing we learned about is standardizing. And that when we standardize a value, we convert it to standard deviation units. Typically how we do this is we found a z-score. And with z, we took our x minus the mean and over the standard deviation. We've been doing that the whole year. Hopefully you feel good about it. Now you can use z-scores in non-normal situations. Say if it's a heavily skewed distribution, you can still find the z-scores. You can't find the percent, but you can find the z-scores. Now, a density curve helps us find percentiles. It's a curve that's always on or above the horizontal axis, and the area underneath it is always 1. Now, keep in mind this density curve describes the overall pattern of the data, and no data set is exactly described by a density curve. It's always an approximation. Now, if the data is skewed, like a long tail to the right, keep in mind that the median is going to be pulled towards that tail, and so the mean is going to be bigger than the median. I think I said that right. The mean is going to be pulled towards the tail, so the mean is going to be bigger than the median. Normal distributions are a special type of bell-shaped curves. They're symmetric. They have the same overall shape, and we use the mean as the center. Sigma is the standard deviation. Sometimes they can be pretty wide, sometimes they can be short, and when they're shorter, that means they're going to be taller. There's a basic rule, we call it the empirical rule. The empirical rule states that 68% of the data in a normal distribution is within one standard deviation. So z-score of -1 to 1, that's about 68% of the data. 95% of the data is between a z-score of -2 to 2. And just about all of the data, 99.7% of the data, is within 3 standard deviations. Now, one standard deviation falls at the inflection point. So when it changes from concave down to concave up, that's where one standard deviation falls. Every type of normal distribution can be converted to a standard normal curve where the mean is 0 and the standard deviation is 1. And this is where our z distribution comes from. And when we look at our tables. Now, consider this problem. Babies are born in the normal range, have a mean of 3,432 with a standard deviation of 482. So what's the probability that a randomly chosen baby is less than 4,000? That's to find the probability that our x value is less than 4,000. Now we convert that x value to a z value by taking that x value minus the mean all over standard deviation. And now we have to do some subtraction. And then we get ourselves a z-score. Our z-score is negative 6.29. Did I do that right? Nope, I forgot 4,000. Let's do that one more time. 34, 32 divided by 482, 1.17. So our z-score has to be less than 1.17. Now, we can use a table, or we can, typically what we do is we hit second vars or variables to the distribution. We do normal CDF, and we go from negative infinity all the way up to 1.17. And it looks like 87.89, so almost 88% of the data is less than that. Now, what is the 30th percentile for those babies? Now, if I draw out my normal distribution, where here's my mean, 30th percentile makes up about that much of the data. So if we have both data points here, what I would type in my calculator is inverse norm of 30% with my mean and standard deviation. And get second vars, inverse norm, 0.3, comma, 34, 32, comma, 482. So 30% along the way is 3,179 grams is the 30th percentile for weight. All right. Now typing this into your calculator, you can do normal CDF, min and max if it's standardized. That means if you have the z-scores. If it's not, if you don't have your z-scores, then you could do min, max, then you type in mean and standard deviation. For inverse norm, if you took inverse norm of a percentile, you would get the standardized answer, which is a z-score. If you took inverse norm percentile, comma mean, comma standard deviation, that will give you the actual value, like we just did on the last problem. The last thing in chapter 2 is to assess normality. One way that we do typically is we look at the box plot of the data. If there are no major outliers or skewness, we can assume that the data is approximately normal. Now, if another way you can do it is to create a normal probability plot, and those are on our calculator, and they should look something like this. If the normal probability plot is linear, then we can say that the data is approximately normal. And that's just what they said. All right, and that's chapter 2.